we're going to derive the multilayer perceptron. And what I'm showing here, above here, is this problematic X-off target function, okay? Where you have two lines crossing opposite regions are the same classification, opposite minus, opposite plus. Okay. Now, it's interesting to observe that this complicated target function can be decomposed in some sense into two pieces where one of the pieces is this line, so that's a linear perceptron, and we can definitely implement that guy as the sign of W1 transpose X. So let's call this perceptron H1 of X. Okay? And the other part of this complicated X-OR function is again, a linear perceptron, this guy here. And that again, we can definitely implement with a perceptron, H2 of X, which is the sign of W2 transpose X. Okay, so, and I'll explain shortly why, this decomposition helps us a lot. But before we get there, I want to show you a nice, convenient visual way of, looking at perceptrons, okay, of representing perceptrons. And that'll be very helpful for sort of following what we're about to do with neural networks. It turns out that, the sort of easiest and most pleasing way for us to talk about neural networks is using a graphical visual representation of neural networks. So let's start with a graphical visual representation of the perceptron. Okay. So here we're taking sign of W1 transpose X, okay, where X is X1, X2. Okay. Now, this visual way of representing this perceptron is to say, well, we have, an initial weight, W0 here, okay, and then the weight that multiplies X1 and the weight that multiplies X2. Okay. So the way I'll represent that is, I'll put in a 1, this is our augmented 1, okay, here we have X1, and here we have X2. Okay, so think of that as the input. Okay, now each of these gets multiplied by the corresponding weights. Okay, so they get multiplied by, W1, if I wanted to call it 1, 0, W1, 1, and W1, 2. Okay, so, okay, and then you take this input multiplied by its weight, take this input multiplied by its weight, take this input multiplied by its weight, and sort of feed that in to the sign function, okay? And out pops the sign of W1 transpose X. Okay? So this is a nice visual graphical view of what's going on in a perceptron. Think of it as you take inputs, you pass them along edges. These edges have weights. The weights multiply what's being passed along the edges, multiply. You add them up at this node. You pass it through the sign and spit out the final result. Okay, and we can represent this guy as well. So you have, 1, X1, X2, okay, and same thing, okay. Send it into the sign function, okay. And you output the sign of W2 transpose X. And so on here are the weights W2. Okay, so this is a nice visual representation. Now, you might wonder, well, why did I decompose this complex function into simpler things? Because as usual, when you try to solve a complicated problem, first, analyze its simpler parts. Okay, and now specifically, mathematically, why this decomposition is useful is because, look, if we call this the target function, okay, f of x, okay, then f of x is equal to, so in this region, h1 is plus 1 and h2 is minus 1. Okay? So you could think of that as h1 is plus 1 and not h2 is plus 1. So this is h1 and not of h2. And in this region, h2 is plus 1, okay, and h1 is minus 1 in this region. And we will say, so either, for f of x to be plus 1, either h1 is plus 1 and h2 is minus 1, or, okay, h1 is minus 1 and h2 is plus 1. So think of this as the AND of h1 and h2 bar. Okay. And think of this as the AND of h1 bar and h2. And here I have an OR. Now this is sort of somewhat standard notation in computer science and electrical engineering, where we represent AND by multiplication and OR by addition. Okay, and I will formally define these things right now. Okay, but for the moment, we can see that using the and the OR operator, okay, we can decompose this complicated target function into and ORs of these two simple functions. And the reason we're doing this, okay, is because these simple functions are perceptrons. Okay. Now, let me formally define and OR. Okay, so and of, let's say, and I'll give you the full definition, the and of any number of inputs, x1, x2, up to xd. Okay, the and of any number of inputs is equal to plus 1 if all the inputs are plus 1, x1 equals x2 equals xd equals plus 1, and minus 1 otherwise. Okay, so it's a standard AND function. Think of plus 1 as positive, okay, and minus 1 as 0, or plus 1 as true, or minus 1 as false. So the AND is true, the AND is plus 1 if all its inputs are true, if all its inputs are plus 1, and otherwise it's false. Okay? And the OR of x1, x2, and so on, xd, okay, is very similar. Okay? The difference being that the OR is true if one of its inputs are true, and it's false only when all its inputs are false. So it's minus 1 if x1 equals x2 equals ... equals xd equals minus 1, and it's plus 1 otherwise. So there, I formally defined for you the AND and the OR. Okay. Now, let's consider, so where are we going here? So why am I introducing you to all kinds of weird stuff? Okay, I'm introducing you to Boolean functions, okay, and we decomposed f into linear perceptrons, okay, which have this nice visual representation, very nice. Okay. And okay, there seems to be a reason to do this because the target function can be reconstructed using these simple hypotheses, these simple functions, and Boolean operators. Okay, so that much we have, but so what? Who cares? Okay, and here's the punchline. So punchline. Okay. And OR, these guys are linear perceptrons. And OR are linear perceptrons. Okay. Bam. And so now the fog should slowly be clearing. Okay. So if H1 and H2 are linear perceptrons, and the ANDs and ORs are linear perceptrons, okay, then F is somehow a complicated combination of all kinds of linear perceptrons. So let's prove this. Okay. So pop quiz / exercise. Okay. So in this visual representation, let us consider the AND of two inputs, and it generalizes easily. So the AND of two inputs. So 1, x1, x2. Okay, so the AND of two inputs. Okay, and we're going to pass this through a sign. Okay, and what's going to come out of here is the AND of x1, x2. Okay, and the OR is going to have a similar visual representation. Okay, so 1, x1, x2. We're going to pass it through weights, multiply, and then send it into this sine function. And out should pop the OR of x1 and x2. Okay. So exercise and do it. Pause the video and just do it. Okay. What should we place on as edge weights? Okay, just like we discussed here. Okay. So what should we place as edge weights? Okay, in order to implement the AND as a linear perceptron, and in order to implement the OR as a linear perceptron. Okay, so work it out. I'll give you a few seconds. 1, 2, 3, 4, 5. Okay, so if you worked it out, great. If you're here just for the ride, okay, please pay attention because this is important. Okay, that Well, the specific weights are not so important, but the fact that we can represent and or as linear perceptrons is important. Okay? So how are we going to do it? So let's think about this. Okay? So and has to be +1 only in the situation where all of these are +1. Okay? So here's what I'm going to do. I'm going to add a weight of +1 here, +1 here, okay, and -1.5. Now let's see, does that work? Okay, if one of these is -1, okay, then these two sum to 0 and you get a -1.5 coming into here and you get -1. Okay. If both of these are -1, it's even worse. The only way that the thing coming into this sine function is positive is if both of these are +1, in which case they counteract this -1.5, feeding in 0.5 here. Okay. And now you feed in 0.5 here, boom, out comes +1. So this perceptron implements the AND. Okay, so now hopefully if you didn't do the OR, you are now ready to do the OR. I'll give you another couple of seconds. Okay, here, 1, 2. Okay, so let's do the OR. And the OR is the opposite. Okay, if both of them are -1, that's the only situation where you will output -1. Okay, so what I'm going to do is I'm going to add a weight of +1.5. You can think of this as a bias of 1.5. Okay, and now I can add weights of +1 and +1 here. Okay, and what we will see is that, okay, the only way in which you can get a negative input into this sign is if both of these are -1. Then you get -2 plus 1.5 gives you -0.5, and the OR produces -1. In all other situations, this plus 1.5 can counteract what's going on here, so that what's feeding into this sign is +1. So, if we wanted a mathematical prescription and of x1 and x2, and of x1 and x2 is exactly the sign of -1.5 plus x1 plus x2. And OR of x1 and x2 is equal to the sign of 1.5 plus x1 plus x2. Okay. Now you should easily be able to convince yourself that we can represent the general and OR of D inputs using a perceptron. Okay. So at least we see that and OR are perceptrons. Okay. So, having proved that, okay, I'm going to erase this. Okay. So all we really need is the facts that and OR are perceptrons. And now I'm going to show you how to implement f of x, okay, only using perceptrons. So let's erase. Now I'm going to show you that f can be implemented using only perceptrons. F of x, the target function f of x, can be implemented using only perceptrons. And here's the basic idea. So the first observation is that f is the OR of two things. If I had those two things as inputs to a perceptron, okay, then I can create the perceptron to implement the OR of those two things. What are those two things? H1, H2 bar, okay, and H1 bar, H2. So let's just imagine that I have those as inputs to my perceptron. Okay. So I have as inputs to a perceptron, okay, H1, H2 bar, and H1 bar, H2. Okay. And let's augment with a 1. So we always, have this augmented 1. Okay. And I want to take the OR of these two inputs, and we know how to do that with a perceptron. We just discussed that. Okay. So I'm going to have weights feeding in to the sine function, and the output is going to be f of x. Fantastic. And we know how to set these weights. These weights are plus 1.5, 1, and 1. Okay. And now I'm implementing the OR of these two inputs, which I don't know how to get them yet, but I'm just assuming that if I had those, okay, then I could implement the OR using a perceptron. Okay, fantastic. Okay, but what is H1, H2 bar? It's the AND of H1 and H2 bar. Okay, and what is H1 bar, H2? It's the AND of H1 bar and H2. And we know how to implement AND with the perceptron. Okay, so what I want to do, Okay, so and what would be the inputs? Okay, so it looks like the inputs are H1 and H2. Okay, well, technically H1 and H2 bar, but it's easy to convert H2 to H2 bar, because H2 bar, the negation of H2 is just negation. Okay, so plus 1 becomes minus 1 becomes plus 1. Okay, so if I have inputs H1 and H2, I can easily compute the negation of H2. Okay, and and then I can easily compute the AND using a perceptron. Okay, so let's see how that would work. So here, if I have, imagine that I somehow had constructed the inputs 1, H1, and H2. Okay, then the AND perceptron, okay, has, minus 1.5 here, 1. Okay, let me do it in blue. It's going to be useful to do it in blue. So the AND perceptron has, minus 1.5, 1, and 1. That would be taking the AND of H1 and H2. Send it through the sign, and what comes out is the AND. But I need the AND of H1 and H2. Bah! So what should I do? Think about it for a couple of seconds. 1, 2, 3. Okay, I gave you 3 seconds. Well, the AND of H1 and H2 bar, I have to first negate H2. Okay? But that just means multiplied by minus 1. Okay? So multiply by minus 1 and then multiply by 1. That's the same as just multiplying by minus 1. Change this sign to minus 1. Okay? And now send it in here. And instead of, so, and if I indeed, have these guys H1 and H2, and now I send it through the sign here, what will be coming out is exactly the AND of H1 and H2 bar. Let's use the same idea to compute the AND of H1 bar and H2. Okay, it's not going to be hard now because we've done it once. So I'll use red. So here, I'm going to have weights, okay, edges, okay, and this is another AND, so it's going to be minus 1.5. Okay. Now, if I were computing the AND of H1 and H2, these weights would both be 1. But I need the negation of H1. So this weight becomes minus 1, and this weight becomes plus 1. Okay. If I wanted to be sort of, meticulous, I would put plus 1 here. Okay. And here, I would put plus 1. Okay. So, if I had H1 and if I had H2 as inputs, I can implement 2 ANDs, which are just perceptrons. Okay. That gives me, so here, I need to now compute the sign. So that gives me H1 and H2 bar going out of here, and that gives me H1 bar and H2 going out of here, and I can implement the OR, and we're all set. Boom, I've got f of x. Okay, good. But so what? We still need H1 and H2. But H1 and H2 are perceptrons. That was the whole reason why we decomposed this f of x into 2 lines, because we can implement those 2 lines as perceptrons. So I can indeed get H1 and H2. Okay? From what? From my inputs x1 and x2. Okay? So here is how. 1, x1, x2. Okay. H1 is a perceptron given by the weights W1. So, W1, you just heuristically put W1 for my weights here. Instead of it now and take the sign, what's coming out of that node is exactly H1. Because by construction, H1 is a perceptron. Similarly, okay, H2 is also a perceptron, but it has different weights. So H2 is also a perceptron. Okay? But it has different weights. Okay? And those weights are W2. Okay? And now I send it through the sign. And indeed, I have H2 coming out of here. Okay? Then coming out of here will be, by construction, will be H1 and H2 bar. And this will be H1 bar and H2 coming out of here. And then this takes the OR. So coming out of here will be H1 and H2 bar or H1 bar and H2. Exactly the function f. Boom. Okay. I have computed f. using only linear perceptrons. Okay. So check. Check. Okay. But let's see what it entails. And this is the real punchline. So I started with my perceptrons H1 and H2. Great. Okay. And those became, you can think of it as the first layer perceptrons. Okay. I put on top of that, in other words, I cascaded this with another set of perceptrons. You can think of that as my second layer perceptrons. Okay. And then I cascaded these two perceptrons with a third layer perceptron. Okay. So in order to implement this fancy target function, what did I need? I needed the ability to cascade layers of perceptrons. Okay. I needed the ability to cascade one layer of perceptrons into another. So I have multiple layers of perceptrons. What did I need? What did I need? The ability to use multiple layers of perceptrons. Multiple layers of perceptrons in sort of this cascade fashion. In a cascade fashion. Okay. And hence, so the original guys are called perceptrons. Okay. And this is called the multi-layer perceptron. The multi-layer perceptron, or MLP for short. Okay. MLP. Okay. And that gave me the power to implement this more complicated target function f. Okay, so I needed the ability to, cascade multiple layers of perceptrons, and also I needed the ability to be able to set the weights on these edges. Okay, so that's what we mean by using combinations of perceptrons. So each perceptron can have, in theory, its own set of weights. Okay, so I change the weights on each perceptron to accomplish goal, i.e., reproduce f of x. So I change the weights on each perceptron in order to reproduce goal. Now it turns out that the perceptrons in the final layer is just one perceptron, which is an all. Okay? But the perceptrons in this layer, the second layer, are all different in the sense that they can be different ands. Okay, so you see the weights are different going into this node versus going into that node. Okay? And here they're clearly different because they depend on what these lines are. Okay. All right. I'll just make a couple of observations. Okay, a few observations about multi-layer perceptron. One. Okay. Well, the last layer is an OR. Last layer is an OR. Okay. It's an OR of what? It's an OR, okay, that is taking an OR of sort of the representation of each plus region in my function. So here I have, in this plus region, it's H1 and H2 bar. Okay, H1 and H2 bar. So H1 is positive, H2 is negative. Here, H1 is negative, H2 is positive. So each of these plus regions, okay, are coming in as a separate input, and then I take an OR. So the last layer is an OR of the positive regions. Okay. So if I had had more positive regions, I would have just had a wider perceptron here because I need more than two positive regions. Fortuitously, I had just two positive regions here. But you could imagine that you can have more than two positive regions. You can even have fewer than two positive regions. Okay. The number of inputs in this second layer, okay, corresponds exactly to the number of hyperplanes, the number of linear perceptrons that I need in order to decompose F. So here I have H1 and H2. So that's my second observation. My second observation is the number of, let's say, the width, the number of inputs into the perceptrons in the second layer, number of inputs to perceptron in second layer equals number of perceptrons used to decompose the target function f that I was interested in. Okay? So you have your inputs that are feeding in with the corresponding weights for each perceptron that is used to decompose f. So you have a set of weights for each of the perceptrons used to decompose f. Okay, and okay, so those weights are all different, and then you take these inputs that are used to decompose f and combine them into ands. Okay, and then you take one final OR. So the final multi-layer perceptron has, okay, so the input layer we typically don't count as a layer, has 1, 2, 3 layers. So the final perceptron has 3 layers. Okay, and so in here we have the number of nodes is equal to number of perceptrons in F, and in here we have that the number of nodes is equal to the number of positive regions in F. And you can see that what's going on here is an OR of the positive regions, where each positive region is an AND. So we're taking an OR of ANDs. That's very related to a sort of technique in computer science called DNF, disjunctive normal form, OR of ANDs. And basically, from sort of circuit theory or the theory of Boolean functions, we know that we can implement any Boolean function as an OR of ANDs. Where the Boolean function is a Boolean function of, let's say, D inputs. You can implement any Boolean function as an OR of ANDs. So that sort of hints that maybe we can implement any function. So let's move to the next sort of surprising conclusion, and this is a really surprising conclusion. Who cares about this function in practice? In practice, we have an arbitrary target function represented by a data set. Okay, we need to be able to fit that data set. Okay, even better, we need to be able to fit that target function. So can this cascading methodology work for more general target functions? Okay. So what we will do is we will prove by picture, you can see the text for more details, okay? But we will prove by picture that this 3-layer multi-layer perceptron architecture is sufficient for essentially fitting any target function, for essentially fitting any data set. That's the miracle of today. This 3-layer multi-layer perceptron, this multi-layer perceptron with 3 layers is sufficient to basically do anything. That's how powerful this strategy of cascading perceptrons is. And if you give me more layers, i.e. if you go to the deep network, you're giving me way more power. It turns out that I can even get away with just 1 extra layer. So this 1 extra layer, it turns out, is sufficient. But we will show that 3 layers is sufficient. It takes a little bit more work to show that 2 layers is sufficient. Okay? So you don't really need deep networks. You can do things with shallow networks if you give me as many nodes as I want in each layer. That's what we'll show next by picture. Okay? So it's an interesting challenge for you. So take your favorite application where you're using a deep network and see if this theorem really holds that we're about to demonstrate. That you don't need that deep a network. You can do it with a shallow network if it's wider. And how much wider you need? Well, we don't really understand too well the relationships between the width and the depth. Okay? But theoretically, you don't need depth. Sometimes we find that it might help in practice, but you don't need depth theoretically. Width is enough. Okay? So let me demonstrate that theorem without proving it rigorously, okay? And then we will move on. Erase. Erase all this.